Formation of the enolate is the first step in this reaction between the benzaldehyde and acetone. Acetone has alpha hydrogen, so when you mix it with sodium hydroxide, one alpha hydrogen is going to be removed, and it forms enolate ion. Enolate has two resonances. The name comes from this resonance that looks like enol losing one hydrogen, and action comes from this resonance because carbon carries a negative charge, is acting as a strong nucleophile, and it can attack any carbonyl compound, including the benzaldehyde that we have on the board. So when the nucleophile of enolate attacks the benzaldehyde, carbonyl group from the benzaldehyde, because carbonyl group already has 4 bonds, the pi bond is going to break. The pair of electrons you have on the enolate is going to be consumed to form the new bond between carbon from enolate and the carbon from the carbonyl group from the benzaldehyde. Basically, the red color is the new bond that is forming. The pi bond breaks over the oxygen, and it gives you alkoxide here. Before protonation, you just have a negative charge here. And when you protonate, you would end up with the OH. OH in beta position. So you have beta hydroxy ketone. The beta hydroxy ketone in the basic solutions that you have will go through dehydration, and you would get carbon-carbon double bond here. This compound is more conjugated than beta hydroxy ketone. It's going to be more stable than beta hydroxy ketone, and you can actually see this reaction taking place without any additional effort or forcing the reaction. If all these steps, if repeat, what does it mean if we repeat all these steps? That means we bring another molecule of sodium hydroxide to remove the hydrogen, remove alpha hydrogen in this step. When you remove the alpha hydrogen, you will get enolate ion forming, except that now your enolate ion is a larger group with a negative charge. So you get this enolate ion forming. Enolate is going to form bond with another molecule of benzaldehyde. Enolate is going to form another molecule of form bond with this benzaldehyde. So pi bond is going to break over the oxygen, and you get, as a final product, it will be like dibenzalacetone. So the intermediate for this is going to look like another alkoxide again. I'm just going to write the steps. You get the negative charge here. You get the CH here, CH2, CO double bond. Okay, that's your intermediate compound. After you protonate this, you would get a again beta hydroxy ketone on this end. After dehydration, you would get a CC double bond, formation of a CC double bond here. So this would be your final product. We use the mole ratio properly. So our mole ratio is 2 moles of benzaldehyde, 1 mole of acetone required based on the chemical reaction. Is based on chemical equation to go from those reactants. So final product, you need 2 moles of benzaldehyde for every mole of acetone. But we are using in this experiment a slightly more than 2-to-1 ratio. And the reason we are using more than 2-to-1 ratio, because benzaldehyde, if it's left in the bottle, if the bottle has been opened or if it's been purchased for a long time, it can be air oxidized. And when benzaldehyde air oxidizes, it would change to benzoic acid. So benzaldehyde After it's being air oxidized, it will change to benzoic acid. Now, benzoic acid, that's not what we need for our reaction. So if you have benzoic acid, it's not going to react here. So whatever percentage of benzaldehyde that has changed to benzoic acid is not going to react. So if you only put 2 to 1 ratio, 2 moles of benzaldehyde, 1 mole of acetone, you may not have enough of the benzaldehyde. So that's why I'm using, based on the procedure, I'm using a slightly more, so 2.2 or 2.1, or at least 2.1 mole of benzaldehyde for every mole of the acetone. If we have the benzoic acid, we can test with 2 ways. We can do IR. For IR, you would get broad peak of this OH between 25 to 3500. You can find the pH of benzoic acid is more acidic than benzaldehyde, so the pH would be lowered. So those are different ways that you can identify you have a benzoic acid has formed or not. And the if it has formed, how would you purify your benzaldehyde from benzoic acid? What is vacuum? Vacuum filtration? No. It's not vacuum filtration. It is using vacuum, but is using vacuum distillation. And that brings an AOH extraction and vacuum distillation. Yes, vacuum distillation. Vacuum distillation, how is that different from from regular distillation, steam distillation, or from the simple distillation or fractional distillation? When you apply vacuum, it's going to lower the boiling point. So you basically, at the end of the distillation setup, I always use like a vacuum adapter that was like a curved glass piece joint, and then that they had extension. That extension, if it's attached to vacuum, is going to lower the boiling point. So basically, instead of applying 200 degrees Celsius for the boiling point to get the distillation done, you are going to lower the temperature. What's the benefit of low temperature is to make sure that you don't spend too much energy. At the same time, you do not decompose your compound. So you don't want to decompose the compound at high temperature. It's used for anything that has high boiling point. Any liquid that has very high boiling point, vacuum distillation could be used properly. One of the suggestion was, can we use PCC? PCC cannot be used here. PCC is going to oxidize primary alcohol to aldehyde and secondary alcohol to ketone. So primary alcohols to aldehyde in general, and secondary alcohols to ketone. So if we use it here, since is the oxidizing agent, is not going to reduce the carboxylic acid to bring it to benzaldehyde. Is a good suggestion because you are trying to reduce this. So to reduce this, you have to use a strong reducing agent. There is a problem with reduction of benzoic acid in presence of benzaldehyde because you have to use very strong reducing agent like aluminum hydride, lithium aluminum hydride. And if you use that strong reducing agent, it would definitely reduce the benzaldehyde. So your benzaldehyde is going to be reduced to alcohol, and this is going to be reduced to aldehyde. Then you lose more of the aldehyde. Good suggestion, but it doesn't work in this case. For reaction, we are going to start with we are going to follow the procedure. You are going to help me to follow the procedure. I just want to make sure that you know the mechanism for the reaction, how is, what are the steps, or if it says to summary or repeat steps, that's what it means. You are going to repeat the steps, basically using more sodium hydroxide to remove the second hydrogen from acetone to change to the enolate again, and then the reaction would continue. The do you have any questions about the pre-lab before I move to procedure? The final product. Do you know what should be the melting point for the final product? Melting point for the final product, 80 to 120. That's not the actual number. It's saying that if you get a range of 80 to 120, that means your experiment is correct. That is a very broad range of the melting point. 110 to 111. Okay, you have sharp melting there. That's more. Yes, that's good. That is if that is the melting point, and you get your melting point for your final product. When you measure the melting point, if you get the melting point of let's say 100 degrees Celsius, what does it mean instead of 110? That means your sample is not pure. If you get a broad range or you get low melting point, either one, so 2 to 3 degree range, it is considered sharp and is considered pure compound. But anything other than that, anything like if you have lower melting point, or if you have a broad range of melting, it means your sample is not pure. And that's the answer to that question. And techniques, we talked about that. If you want to get the benzalacetone, if you want to get this as a final product, this compound as a final product, you have to use less of the benzaldehyde, so it doesn't go completion for two benzaldehyde being consumed in the reaction, because for final product you need 2 benzaldehyde. If you use a 1-to-1 ratio, it will give you 1. Okay. Any questions about the theory of the experiment? So what technique are you using to identify your final product today? We are using IR. What do you expect for the IR? I don't know if IR has been covered in lecture or not, but if it's been covered, what do you expect to see in the IR? This is your final product in the red box down here, up here. If you can see, that is your final product. Yeah, CO double bond, CC double bond benzene ring, CC double bond benzene ring. Basically, you have to look for point of difference. You have to look for the difference between the IR of one or both of the reactants and the final product. What do you want to see as a point of difference that, let's say, benzaldehyde doesn't have or acetone doesn't have, and you would see a point of difference using IR. I missed it probably. You gave me an answer. I missed it. Let me go to chat room and I look at your answers. Appearance of the carbonyl absorption. What do you expect? So you don't want a peak between 2500 to 3500 because that would be for carboxylic acid. If you want a 1710, okay, 1710, both of your reactants is going to show that peak at 1710 for carbonyl. So that's not point of difference. So what are you looking for? Can you see what has happened to your reactant? First of all, can you tell me if the IR has been covered in lecture or not? For some of you, at least? Okay, good. So how does electron withdrawing group affects the absorption of a peak in IR spectrum? So if you have a, let's say, carbonyl group and you add electron group to that carbonyl group, what happens to the carbonyl group? Which way would it shift? Okay, it shifts to the, if you have electron withdrawing group, it would shift to higher numbers. And if you have conjugation, resonance or conjugation, the carbonyl group is going to shift to lower numbers. So conjugation lowers the peak absorption, and electron withdrawing is going to increase that wave number, or the absorption is going to take place at a higher number because your bond actually gets more of a ionic or more electrostatic attraction is going to appear there. Now, what is happening here for your final product? Your CO double bond is conjugated here for benzaldehyde, but is super conjugated for dibenzalacetone. So if it's super conjugated, you see that it's conjugated with this CC double bond, and CC double bond is conjugated with 3 double bonds in the benzene ring. CO double bond is conjugated in this end on the left side with the CC double bond, which is conjugated with 3 pi bonds from the benzene ring. So we call this one a super conjugated CO. So your reactant has conjugated CO, but your product has a super conjugated. For the carbonyl, you get peaks for hydrogen and you get peak for CO. So for aldehyde, you would get 1700 or 1710, around 1710. You get 2700 and 2800. So you have set of 3. You have set of 3 numbers for aldehyde. For carbonyl, and then you have your hydrogen, 2700, 2800. For the product, when you come to the product, you don't have aldehyde anymore. So these should disappear, and 1700 should shift to less than 1700. So the CO double bond should be less than 1700, and less than 1700, it could be like 1680, 1690, and anything less than 1700, it's acceptable, and it's going to prove that your CO double bond nav is super conjugated, and you don't see these peaks, then you know that your compound is free of any benzaldehyde. So benzaldehyde is purified from your product, and the final product has formed. Okay, let's start the experiment. This experiment, there is a step that you have to get rid of OH, or basicity of the substance, and that takes a very long time. So we are going to start the experiment so we can at least finish in the given time for the lab. We go to the setup here, and step by step. What should I repeat again? The conjugation. Conjugation is going to lower the frequency. Electron withdrawing group is going to increase the frequency. So for CO double bond that is in aldehyde, if it shows around 1710, when it comes to dibenzalacetone, for dibenzalacetone, you get less than 1700. So that could be like 1680, 1690, but it is going to be less than 1700. And the reason for that is you have your CO double bond is super conjugated. You have double bond, like 4 double bond on the right side, conjugated, 4 conjugated double bond on the left side. So your carbonyl group is super conjugated. And if it's super conjugated, the CO double bond in the IR is going to show much lower number or wave number for the absorption. Okay, approximately 1.2 grams of acetone. So also calculate the volume of exactly 4.9 grams of benzaldehyde. Into 125 element flask. So I'm going to get the chemicals for you. So I'm just measuring chemicals. Remember, 40 moles of sodium hydroxide and 30 moles of ethanol, and I'll be right back. I'm just going to measure that in the input. And then I will write and we are going to place an ice pack. I place that in ice bath. What's the next step? Benzaldehyde to the flask. Okay, how much of benzaldehyde should I use? What's the volume? Do you have it? That's the gram. Do you have the volume for benzaldehyde? Did anybody? Okay, volume would be 4.3 liters of benzaldehyde. Okay, going to get the 3.4 milliliters of benzaldehyde. Okay. The way the procedure is written, can you tell me which one is the limiting reactant, which one is excess compound? Is benzaldehyde limiting or the acetone? Benzaldehyde limiting. But when I'm measuring like graduate cylinder for benzaldehyde. I'm using graduate cylinder for benzaldehyde. But then the next step is telling you to measure exactly 1.218 grams, right? So normally for the limiting reactant, you have more exact. So based on how it's written, you should kind of identify that acetone is limiting reactant. But the best way to identify it is to get the number of moles, and then from the number of moles, you compare it and see which one is the limiting reactant. I changed the number for grams of acetone in question 1 to like 4.8 grams, but I think for the quiz, I didn't write that number. I think I wrote it as a 4.3 instead of 4.8. But still, benzaldehyde is supposed to be, in this experiment, is supposed to be the excess compound, and acetone is the limiting reactant. Okay, next step. I'm mixing it for now. You can take a screenshot of the sample being mixed before adding I added already. I added the 40 milliliters of sodium hydroxide, and I added the 30 milliliters of ethanol. I add benzaldehyde already, and it is mixing. So our next step is to add the acetone. Now, to add the acetone, just going to take the flask, place it on the balance, on the scale. Press the tare button to make it 0. And this is one of the easiest way to measure exactly 1.218, because if I measure the 1.218 in a small beaker, by the time I bring it from the scale to my flask, some of it would evaporate because it's acetone. It's just like nail polish removal. It would evaporate quickly. If I add it to a solution, because it's mixed with with the ethanol and with the sodium hydroxide, which is basically water. Now the rate of evaporation also is not going to be as high. So also I'm measuring exactly 1.218 gram here, because if I transfer some of it, it would be left over. Some of it would be left over in the container that I'm trying to transfer. So this is like directly measuring. You could take another screenshot now with the measuring the 1.218. I'm just going to add enough until it shows 1.218 or a number close to that. There's no guarantee that it would be exactly that number because of the size of the drop, but I try to stay as close as possible to that number. Okay. I add the 1.218 based on the procedure. And why does it have to be exact? Because that's my limiting reactant. But when I was explaining how I'm adding exactly 1.218 by placing the liquid already on the balance pan and adding drop by drop to reach the mark of 1.218. So the number wasn't actually 1.218. It was 1.224. Yes, the mixture is being stirred now. And as the mixture is stirring, it is showing the product formation of the product is getting cloudy. A yellow precipitate is the product. It shows the formation of the product as it forms, it isolates. So you see that. So we are going to time it. Let me see what time we start so I can. Okay. From the time I added, it was like 109. Okay, 109, and then we are going to keep track of the time for now. 108, between 108 and 110, but from the mixing, when I start putting on the hot plate for stirring, it was 110, but from the time I mixed it, it was 108. Okay, last time I told you about the mass of the product, and I kept the product. I'm going to bring the product and measure it again. I want to see if there was any change and if it did dry more and if it lost more mass. Do you remember the product from last class? I said because the particles kind of they were very pasty and they trap water. The mass we couldn't get like a dry sample. So I'm sure for those of you who did the calculation for the percent yield, you got higher percent yield in your report. Is that right? Yes, over 200% yield, some of you. So if you measure the mass again now, is a 51.54. That less than the last time. Do you remember what was the mass last time, or I need to go back and check it? Do you remember the value from last class? It was 53. Okay, 53. So now is a 51.542. So you can record that number. This product actually requires more of a overnight drying. Sometimes I use the oven. And it did work when I did a small sample for melting point. But when I had all of it in one place, it didn't dry out. Okay, with this number, now the percent yield drops to below 100, so 1.477 gram of the product, and that is more reasonable, right? That is a more reasonable number, and the excess of the compound is coming from the solvent. The excess of the product that you had there is basically coming from the solvent. You are not going to lose point for having high percent yield for the lab report, but I wanted to make sure that you see the difference for some powder or some product. If I tell you, because last semester, or not last semester, I was on sabbatical last semester, I did not teach, but the semester before, sometimes I suggest the class to leave the sample overnight, and it was a question, why do we have to leave it overnight? I need to write the lab report. I don't want to come back, or it's hard for me to come back if it's not the day of my lab. So at least you see the difference now. Sometimes it requires more time to dry a sample, and you should never get higher than theoretical yield. And if you do get higher than theoretical yield, you should never change your numbers. They say, oh my God, it's 200, it's too much. I'm going to change this. Maybe I made a mistake. Maybe I recorded wrong. You should always record the numbers that you see. You should trust your number more than anybody else's data. And then you just have to explain in the conclusion part why you got that percent of error. The percent error, why is like too high of a percent error. So this is proof. So we got that, but I remember it was a long time, about 1996. I was teaching a lab at Miami-Dade College because I was Miami-Dade College hired me first. I was there for 8 years. Then I moved to Broward, full time there, and then I moved as full time here. The student, his name was Lorenzo, and he came to me and says, "Okay, we were doing chemistry of copper." Says, "I got more than 100% recovery. Can I do same experiment with gold and I get more than 100% recovery for gold? So if you start with 1 gram of gold, maybe I get 2 grams of gold." And I still remember it was it was yes, I'm sure, you know, he found a different idea for business, but he was, at least at that point, I made sure that he understands we can't get more than 100% recovery of the gold unless you are an alchemist. And I did tell him that, like, if you are an alchemist, maybe you can, but if not, you cannot create gold from, you know, extra gold if you didn't start with that much of it. So percent recovery, to me, it's not the number, you know, magic number that your grade should be based on, but understanding why you get low or high percent recovery, it's a big deal, based on the understanding of the experiment. Okay. Okay, any questions? Any questions from this experiment or last experiment? Why is cooled in the reaction mixture? Because we don't want any of the chemicals that we keep adding to it. It vaporizes. We want to keep it in the solution form. So if it's not cooled down, like when I'm adding the acetone, while I'm adding acetone, some of it can vaporize. And the reason you cool down reaction mixture is to avoid high heat, like if the reaction is exothermic reaction and is going to generate heat. But in this experiment, that's like in general, but in this experiment, we are trying to avoid evaporation of the acetone, because evaporation of acetone is like, it happens at room temperature. That's why when you have like nail polish, you use that as the solvent to remove, because it evaporates right away, and people have good experience with it. Okay, a next screenshot of the setup. So now you could see the precipitate. It's cloudy formation of this. You can. We are going to use the vacuum distillation, vacuum filtration also, but you can take this as the next screenshot. Yes. Okay, any questions? Sure. Maybe I moved the computer, that's why. Very good. Okay, what are the next steps? So we can get ready for next steps while we are waiting. Yellow product from by vacuum filtration. I'm not using the first filter paper, so I can I don't have to measure the mass, but the second time I'm using the filter paper, I have to measure the mass. Okay, here it says 80 degree for setting up the oven. Can you explain why does it have to be 80 degree? Can I put a higher number to evaporate it faster or to dry it faster? Or can I put at 70 degree and not to take any risk or any chance? So is 80 degrees safe? Would my compound melt in the is not safe? Can I put this oven at 70 degree? No. So I guess your answer is to my the new questions that I cannot put at 70 degree. I know the manual says that I wrote experiment, so I did design experiment. I'm just saying that the why I cannot set the oven. This is oven is to dry the product. Setting up the oven is suggested to be 80. I'm asking why it cannot be 70. There's one answer that at 70 it won't melt. Do we want to melt? Is that good or is not bad? If we're trying to avoid melting of the sample in the oven, should we set it at 70 instead of 80? Can we use 70? What would be wrong if we use 70? I want to see if you can justify why are we using 80 degree or any number for the setting of the oven. We need to remove the liquid in the oven, or are we trying to evaporate the liquid? Okay, we are trying to evaporate the solvent, which is the ethanol, in the oven. So if we are trying to evaporate, what is the number that we should look for? Why it doesn't evaporate at 70? Think we used ethanol for the first experiment? 78 is the boiling point for ethanol, so it is not going to evaporate at 70 degree. So you leave the setting for the oven at 70 degree, is not going to evaporate the solvent. If it's 80, is 2 degree higher than the boiling point of ethanol, it will ensure evaporation. Very good. Yes, it will ensure evaporation. And can I put that 100 degree instead of the 80? No. What would be a possible problem if I set the oven too high? If I put the oven too high, it can potentially melt the substance. If the substance has a melting point of 110, it's not going to boil or evaporate any for close to 100 or 110. Is going to be much higher for boiling or evaporation. But melting, we don't want to melt the product inside the oven. Yes, and if the sample is impure, we still don't want to melt the oven, melt the sample in the oven.
We want to take it out, measure the melting point, then find out if the sample is impure or not. We don't want to melt it in the oven, because if the sample is melted in the oven, we basically lose the sample. We don't have a sample to work with. We need the sample for IR, we need the sample for melting point. Let me go ahead and turn on the oven and set it at 80 degrees. Be right back. And getting ready for next step. Actually, vacuum to the pump and use a filter paper. Okay, do you have any questions while we are waiting for the crystals to form? That was the volume for benzaldehyde. Apparently, density for benzaldehyde is greater than 1. So for 4.8 grams, we have to measure them. We have to calculate the volume. I'm going to try something new today for this experiment. Actually, when I did some research, I found that it's done with in different labs. We always have trouble for this experiment. We always have trouble to get rid of that pH, lower the pH by washing only. And I saw one lab, what they are doing, I think is up north, one of the labs, what they are doing is they are adding HCl to the solution, not at the beginning. I'm not going to add to this. I'm going to continue my procedure, wash the crystals with 100 milliliters of water. And then when I'm washing with 100 milliliters of water, then I want to add few drops of HCl to lower the pH, because by washing, it takes a long time, and students always had difficulty with getting the pH to less than 7 or 7 to make it neutral. And we keep adding like 50 milliliters of water, like over and over. And with the vacuum that we have today, I think it's a perfect timing, because if it was a strong vacuum, based on the size of the crystals we have, it can still make the filtration fast. But for this vacuum pump that we are using, because it's small, is going to be problematic. So I'm using that new trick of adding HCl to the solution to lower the pH today. Let's see if it works, and I'm sure it's not going to affect, definitely it's not going to affect the product, because our product is aromatic, is conjugated ketone. It's not basic solution. It doesn't have any basic functional group, so it's not going to react with HCl. It is stable in both acidic and in basic solution. So since my product is stable in acidic solution, I could add some HCl to neutralize it, rather than just washing. The product is stable in acidic and basic. HCl is stable in acidic. HCl is the acid. The product, which is the dibenzalacetone. Dibenzalacetone, our final product, the yellow color final product, is stable in the acidic solution. So I'm going to add few drops of HCl to neutralize excess of sodium hydroxide after the first filtration and after washing, not right now. Okay, while we have like 3-4 more minutes, for next week, I had some students, they already asked me for lab reports for 17. We don't have a lab report for 17. So what you do instead, you just copy the tables. You do have pre-lab for 17. For 18 and on, we don't have any more pre-labs. So starting experiment 18, we don't have pre-labs. It's going to be just the lab reports. And for the lab report for 18, since there is no copy the tables, is like if you can type it, that's going to be better. If not, just create a table and copy each number and bring it over. For 17 or 18 only, yes, you do have lab reports for 19, and you have lab notebooks. Let me see what I have in the instructions for you. I just want to make sure what I say is same as the instructions that you have for I don't want to confuse you. So for assignment, nitration, what do you have for the instructions? Okay, I have lab notebook 17 and 18. Okay. Instruction for lab notebook 17 and 18, write the experiment. Second, title for the experiment, table for IR NMR values. So that goes to lab notebook. So copying, just write it by hand. No printing out and pasting it. Copy it, just copy. You should write it by hand. And then for 18, a classification test would be, and the solubility chart. The solubility chart in my lab manual is on page 183. The classification tests, I can show you where they are. So IR values are on page 161 for me, or the third page of the experiment 17, and 161, 162, that's the fourth page of the handwritten, yes. Handwrite rather than typing. Typing is fine. That's for lab notebook though, right? Lab notebook, do you type your lab notebook, or whatever you do for other experiment, you do the same? Okay, can you please read the instruction for the assignment that it says lab notebook 17 and 18? Tell me which part is not clear so I can write it clear so everyone gets it. I read the instruction for the assignment multiple times and I am still confused. Okay, how do you want me to correct it? Because I'm trying to correct the instructions. So if it says IR table that you're copying, referring to, if it says IR table, that would be table number. There's no number for the table. It says the functional group here. You see that? It says functional group and then carbonyl absorption, and it gives you the information where would it appear, the numbers, location for those. And then you have more for IR. Okay. For IR. You also have a table for NMR. So these are the tables. So how should I label it that is more clear? Okay, 164, that's fine. Because you're using the e-copy, right? E-book? Okay. So if there is anything, even if it's different, that's why I did not put the page number, but it's coming from experiment 17. Those tables, and you have those tables that is coming from experiment 17. 17 is the tables. So you have one for NMR, and you have like 2 or 3 of them for IR. 2 or 3 small tables for IR. Those are the tables. Okay? So you're going to write these in your lab notebook, and then you take the picture and you upload to the lab notebook assignment page. To type the tables, it's fine, but when you write it, the purpose of writing is just to remember for a longer time. That's all. If you want to type it, it's fine, but then you have to type it, then you have to print it, or you're just going to type up and make a document and upload, is fine. How you're going to put that in your lab notebook though, if you type it only? Then you have to print it, right? But typing is always an option. You can always type instead of writing by hand, and that's not a problem. I don't have any problem with that. A table from a chart, solubility chart from experiment 18. It looks like this. This is the solubility chart. And also, you have the classification test. Classification test, it says, is a titled classification test. So there is really no way around it. You have to read the experiment, the entire experiment. Experiment 18 is very important. So read it, and then when you see like classification test, you have 8 classification tests, and you just copy those. What are the classification tests that you could do for carboxylic acid? What are for hydrocarbons, and what are for phenols? So if you only read the assignment instructions, it may not, if it doesn't make sense. If you go to open the chapter 17 and 18 or experiment 17 and 18 and read the experiment, it might make more sense. But if you have any suggestions, is there any wording or any single word that I should change in the instruction to make it more clear, I could do that. I just couldn't give you page number because the page number for ebook is different from the hard copy, unless you find out those and you give it to me and I add to the instruction. So I can say the IR and NMR from the pages from experiment 17. Experiment 19, that's different story. You do have reports for experiment 19. Yes, definitely. This is just for 17 and 18 that it says no report. Yes, definitely for 19, yes, report. Is it time to stop? Or past the time to stop? Yes, okay. We are going to go back to experiment. Stop the stirring and take the magnetic stir out. Try to take the magnetic stir out. I'm not sure if it's going to come out or not with this. It's very heavy, so I'm going to turn on the vacuum and filter the mixture. Going to use some water to transfer everything to make sure all the crystals or precipitate is transferred using cold water, so to make sure. For washing, always cold water is better. Transfer. Okay. Now that everything is transferred, I'm going to the next step. Next step is asking for washing the sample with 100 mils of water, right? That's on the next step. Going to transfer into a beaker. Okay. Where is the... Okay.
Sample is completely transferred to the beaker. If you keep adding water to the powder that is inside the beaker funnel, the washing part is not going to be efficient. So this is like better washing. We're trying to get all the sodium hydroxide away. And this step is slightly different from what's in the procedure. I'm going to add a few drops of HCl as well to this solution or the mixture. Going to first finish the experiment when we have time to wait for this and that, like for crystals to dry or when they are in the oven. Then I go back to the chat room and I answer the questions or concerns that you might have. I don't want to mix the two things, so I stop talking about 17, 18 at this point. I'm trying to finish the experiment 16. We will go back to experiment 17 and 18 later. Okay? We're just washing with water at this point. And I added a few drops of HCl. We have two choices. We can neutralize it and then drain it, or we can keep washing until all the sodium hydroxide is removed from the product. And if sodium hydroxide is removed from the product, then we get we can do that by neutralization, or we can do that by washing to remove sodium hydroxide. Okay. Before I filter a second time, I have to use a pre-weighed filter paper, and I'm going to ask you to take a screenshot of this. So I take out there to 0. Okay. Mask for watch glass and filter paper. You can take a screenshot. Did you get it? Watch glass and filter paper. Screenshot. Now I'm using the pre-weighed filter paper this time.
asking you to wash more. And the reason we are washing is to make sure that all the soluble impurities, water-soluble impurities are removed. So as I'm washing, I'm also using the washing solution to transfer anything that is left in the beaker. So I don't lose the product, because if I keep losing in every step, then at the end of the day, I'm going to have low percent recovery. I try to minimize those experimental errors. Try to get as much product possible into the filter paper. The vacuum flask is filled up. I have to stop the vacuum. Remove the filter and set it up again. Because if you have too much liquid, it can go back to the vacuum. It can burn the vacuum. Electronics, they don't like to shower. So we don't want any water on electronics. Yeah. So I transferred as much possible of the product. And for the next step, I'm going to wash it with ethanol, which is part of the procedure. I'm going to wash it with ethanol, cold ethanol. Is this one? This is called trap. Yes, trap. So you see that some liquid went in here. You can see some of the liquid went here because I didn't stop when I had like halfway filled. I stopped it when it was almost full to the neck. So some of the liquid went here. If I didn't have this trap, the liquid would have gone into the pump and it would destroy the pump. And I wanted you to see what happens if we continue filtration. We get some of the liquid into the trap, and if we don't have the trap, into the vacuum. Okay, we are in the 5 minutes vacuum, running the vacuum. So we are going to continue for 3 more minutes. This flask is called vacuum flask. The trap, it only traps the water or any solvent. It protects the vacuum from water or from liquid. That's the trap. The Buchner funnel has your product in. Okay? This one has the product. Okay. Has it been 3 minutes since I said we're continuing for 3 more minutes or not yet? Has it been 3 minutes or not yet? No? It's been 3 minutes already? Okay. Okay, if it's been 5 minutes of vacuum, try to remove excess of solvent. And we can stop the vacuum and transfer the product into the same watch glass that we made already. Do we need to get both melting point and DIR or just DIR today? Do we need both or just one? Both? Okay. Okay, going to place in the oven to dry. Just going to leave it in the oven to dry. Going to take a small sample for melting, leave it on the separate paper. Okay. We have about 3 minutes for your questions. And then we are measuring the melting point and finding the IR spectrum for the sample. Do you have a quick questions? Do you have any quick questions? Patient and wait. You can multiply the density by the mass. I'm sorry. You can use the density equals mass over volume to find the volume. I measure the mass directly. You could find the volume, so you know how much of the acetone you need to get from the fume hood to your station or to the balance area. So you don't have to go back and forth. So it's basically approximate number for the volume, because we don't measure it by volume at the end. We measure the mass. Has it been 3 minutes? Yes? Okay.
I'm going to take the sample for the melting point. Okay, the sample doesn't look dry to me. We can leave it for another minute. It's better to start with the dry sample than coming back to wait for. We have some sample here, but it's not my students. I don't know who left it. Looks like from last semester. That sample looks from last semester. We're going to use the sample that we just made. So okay. So measuring melting point. So measure the melting point for the sample. Going to prepare the sample. First, use the capillary tube to get the sample in. drop it through the glass tube to pack the sample and make sure that it goes down. Let's try a new sample. Okay. Okay, I have the capillary tube, the sample in the capillary tube, and place it in. Sample holder or melt temp apparatus, and wait until the sample is melted. We are going to record the melting point for the sample. If you just turn on the computer, that's all. Trying to for the IR. I don't expect it to melt below 80 degree because the oven was 80 degree and it did not melt. That's why I'm not constantly watching. I'm waiting for the temperature to go to like 70, 80. Then I have to monitor it more closely. The setting on the power regulator, I have it between 4 and 5, just like the other one. It's less than 5 this time because the melting point you told me is about 110. Yes, it's an alcohol thermometer, yes. We don't use mercury thermometer unless we really have to. If you have a melting point that is over 260 or for 300,
then we use the mercury thermometer that can go up to like 500 degree. So okay, it's 102. It's not melted yet, which is not bad, but the closer it melts to the real or literature value for melting point, that's indication of more pure and dry sample. So it's better if it melts closer. Okay. Start melting at 104. 104. 108. 104 to 108. Turning off. Taking the sample, capillary tube, into the broken glass box. Now we are going to test for IR. The sample did melt at 104, so that means it has some impurities, not a lot, but some impurities. So we are going to try the IR to see what type of impurities we could get here. So we place a small amount of the sample into the sample holder. And on the computer setting, we should look for the scanning of the product. So this reaction is experiment 16. And what day is today? May 26th. Okay. 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 Top plate installation initializing or top plate missing. I have some problem with the IR, so I'm gonna have to restart. And I hope that I can fix this problem. I will take the IR for you later and I will email it to you. But we also need to measure the mass of the product. So there's more than enough time for the product to dry. Hopefully it's completely dry at this point. We are going to wait for it to cool off slightly until I can touch it without burning hands. I'm going to leave it for sample to cool off. And measure the mass. Okay. Can you take a screenshot of the, this would be the last one. 42.41 or is moving. You got the screenshot? Yes. That's good, yes. So if you didn't get the screenshot of the setting, one more try. The number keeps changing, yes. I'll take it out to make sure it's 0. I took it out to make sure it's 0 again. And put it back up. Okay. 42.230 is the state most often, so we can record these numbers because the sample is more, yes, it's cold now. Yes, 42.230. Perfect. So we have the melting point, you have the mass, you are waiting for the IR. I will email you the IR sample for you, or the IR spectrum of the sample. And you can write your lab report. I'm going to stop the recording, and you had some questions that I need to answer those before I go back to the IR or fixing the IR machine. Okay, going to stop recording.